Rahman Rahim. Hello everyone. This lecture will be about unsymmetrical faults in the power system, and before I go to that topic, I would like to start with symmetrical components. A brief introduction to symmetrical component. So when we have unbalanced three-phase system, which is gonna be, for example, something like this. If this is phase A, B, and C, then these three phases are not symmetrical. For a symmetrical system, for a three-phase system, each phase is 120 degrees out of that phase, of the other phase. So we will have phase A, phase B, and phase C, and they are each apart 120 degrees from the other phases, or 240 degrees. Now, if we have unsymmetrical phases, how can we convert this unsymmetrical system into symmetrical system? There was a method developed by someone, and it is called symmetrical components. And symmetrical components, it's a mathematical expression that relates the unsymmetrical vectors and convert it to a symmetrical vector. So the rule is I of each phase will equal to A multiplied by the sequence phase. So IA, IB, IC as this vector is equal to A, and A is simply 1, 1, 1, 1, 1, and here is A square, A, and then A square. And then we will have called symmetrical sequence network I0, which is zero sequence, I1 positive sequence, and I2 negative sequence. So this is, we have zero sequence, negative sequence, and positive sequence vectors. So what is A? A is a vector which has a magnitude of 1 and the phase angle of 120 degrees. A square will be 1 and the phase angle of minus 120 degrees, or 240 positive. Now to convert from unsymmetrical component to symmetrical components, we simply convert it by taking A inverse, and A inverse is 1 over 3, 1, 1, 1, 1, 1. Here is A square, and A multiplied by phase A, phase B, and phase C. So you're gonna have some examples on how converting from here to here and vice versa. So let's go to the first example. Let's say I have the following currents, which is IC, then I have IA, and IA is 10 angle 0. Then I have IB, IC is 10 angle 30 degrees. IB is 10 angle to 30 degrees. So convert this, or find the sequence network of this symmetrical component of this three faces. So simply we will add I0, I1 and I2 here equal to 1 over 3, 1, 1, 1, 1, 1. Here is A, which is 120 degrees, then 1 to 40, here is 1 to 40, and here is 120, multiplied by IA, which is 10, IB 10 to 30, IC, which is 10 angle 30 degrees. Then we will find I0, which is equal to 1 over 3. Did I wrote 1 over 3 here? Yeah. So 1 over 3 multiplied by 10 plus 1 multiplied by 10 to 30 plus 10 30 degrees. So I will get the answer, which is 4.172 angle minus 12.3. Then I1 is equal to 1/3 over 10 plus 10 to 30 plus 120 plus 10 angle 30 plus 240. So I will get something like 7.69 angle minus 30.6 degrees. I2 is equal to 1/3 10 plus 10 angle 230 plus 240 plus 10, then angle 30 degrees plus 120 degrees. So I will get here the answer is 4.85 angle 98.2 degrees ampere. So I can check for my answer by simply adding IA, which is equal to I0 plus I1 plus I2, and if I add them I will get 10 angle 0. This is just to check your answer. Another example is when I have a delta connected load and one of the phases are disconnected. For example, I have IA, IB, IC. So this phase C is open circuit. So I'm having IC is equal to 0. So how can this affects the fault? So in this I will have like for example, IA is entering and IB is leaving, so IA is equal to, or IB is equal to negative IA. So I'm gonna have symmetrical component for phase A. If I want to calculate phase A, so let me do the calculation. For IA, it will equal to IA 0, which is the zero sequence, the zero component for phase A, which is 1/3 IA plus IB plus IC. Since IC is 0 and IB is negative IA, then the answer is 0. So when one of the phases are open and delta connected load, then the zero sequence component is 0. For IA1 to be 1/3 IA plus A square IB plus AIC. This is 0. Only will end up with this one. And IA2 is 1/3 IA plus AIB plus A square IC. This is 0, so I'll have only this term. Even if the delta load is having unbalanced three-phase currents or voltages, then the zero sequence current or voltage will equal to 0, because if I add IA plus IB plus IC, then we will have 0, because the neutral current is also 0. Here is a third example for this. If I have the following resistive load, and we have a balanced load, 10 ohm resistor. So the 10 ohm resistance, this is phase C, A and B. A voltage applied here to this load, which is unbalanced load. The line voltage VAB is 100. The line voltage VBC is 80.8 and an angle 121.4, and VCA equal to 90 volt with an angle 130 degrees. So how this affects the currents and the power consumption in each resistance. So if I said find power in each resistance. So the first thing, since this is line-to-line voltage, I have to find the phase voltage across each resistance. So I can measure the power across the resistance. So the first thing is to find the zero positive and negative sequence voltages of the line-to-line voltage. So I will have V line-to-line zero sequence, V line-to-line positive sequence, and V line-to-line negative sequence. and this is equal to 1/3, or let's say that I will write it just now A inverse, since you know what is A inverse, and I will put 100, 80.8, 121.4, 90, and 130 degrees. So if I use the calculator, I will get 0 for V line to line 0 sequence, 89.9, 2.89, and then here 11.2 minus 23.9 degrees. Now we can convert this into line to neutral, which is the phase voltage. So V line to neutral 0 is 0. V line to neutral positive sequence is 89.9, 2.89 divided by root 3 multiplied by an angle which is minus 30, and I will get 51.9 with an angle negative 27.11. V line to neutral's negative sequence is equal to 11.2 negative 23.9 divided by root 3, get 6.47 with an angle 6.06 degrees volt. So now if I want to find the power in each phase, it will be V0 squared plus V1 squared plus V2 squared, which is the phase voltages of the symmetrical components, divided by the resistance, which is 10 ohms. So I will get 0 squared plus 51.9 squared plus 6.47 squared divided by 10, which is equal to 273.5 watts in each resistance. So for the three-phase power consumed by this load will equal to 3 multiplied by the 273.5 watts, and this will gives me 820.6 watts. Now I will solve another example. It's the same previous example. I mean, we have the same voltage levels, but here for this load it is grounded through a 2 ohm resistance, and we have been asked to find the line currents instead of the powers. So the same steps we follow here to first convert the line-to-line voltage, unsymmetrical voltage, to zero sequence, negative and positive sequence line voltages. Then we will find the line to neutral voltages. Then we convert the line to ground voltage of the sequence network into line to ground voltage of phase A, B, and C. So since we found this to be 0, 57.9 angle minus 27.1, here's 6.44 with an angle of 6 degrees, 0.1. Now we find VA, VB, and VC, VAN, VBN, VCN, and simply by multiplying A by VLG 0, VLG 1, and VLG 2, and I will get the answer to be 57.42 with an angle minus 23.6, and here it's 52.66 with an angle minus 154.1, and here is 46.26 with an angle of 96.5. Since we found this, we can find the line currents. Our load is balanced load, which is the 10 ohm resistance for each phase. Then the relationship between the current and the voltage is as follows. So we have VAG, VBG, and VCG is equal to the Y-connected impedance plus the neutral. And here's we have ZN, here's ZN, here's ZN, the neutral impedance, here's ZY plus ZN, here's ZN, here's ZN, ZN, and then ZY plus ZN multiplied by IA, IB, and IC. So if I want to find IA, you can see that here is 12, here is 2, 2, then 2, 12, 2, then 2, 2, and 12. IA, IB, and IC is equal to VAG, VBG, and VCG. So the final thing can be noticed here that it's 10 IA plus 2, which is, I took the common factor. If I can expand this with the 3 currents to find VAG, then VAG can be found to be equal to 10 IA plus 2 multiplied IA plus IB plus IC, and VPG is equal to 10 IB plus 2 IA plus IB plus IC, and VCG is equal to 10 IC plus 2 multiplied IA plus IB plus IC, and finally IA plus IB plus IC tend to be equal to 0. So what we will get that IA and IB and IC will equal to the voltage, the phase voltage divided by 10, which is, this will gonna be 5.72 minus 23.6. Here it's 5.26 with an angle minus 154.1, and here it's gonna be 4.63 with an angle of 96.5 degrees in amps. I hope this example gave a good explanation about the symmetrical components and how they can be used to find either the sequence network currents or voltages or the unsymmetrical voltages and currents. And in the next lecture I'm gonna go through the unsymmetrical faults very soon, inshallah.